Case Study R tutorial. We are nearing the end of the course, and as a final exercise in our last week, we are looking at a case study, the Canadian Trial of Dietary Carbohydrates in Diabetes. In the first video lecture, Allison introduced to us the study and a few keywords and concepts that allowed us to better understand the purpose of the study. In the second lecture, you saw how to design such a study to acquire the data needed to answer the research questions. One of the questions raised in this particular lecture video was how large of a sample would we need to be able to obtain statistically significant results? Recall that we wish to calculate the sample size required for a two-sample t-test with a power of 0.8, a difference between treatment means of 0.004, with an estimated standard deviation of the differences of 0.0066 at a 0.05 significance level. To calculate this, we will need to first install the Power package with the install.packages command, and then load the package with the command library. The command we will want to use is power.t.test. This command is very useful in that it can calculate power given the parameters, or it can determine parameters given the power. We will use it to determine the sample size, so we will enter all of the information that was given. We will start with the required power of 0.8. The second argument, d, is the effect size, calculated as the difference divided by the estimated standard deviation of the difference we are interested in. So 0.004 divided by 0.0066. We will specify that it is a two-sample t-test with a two-sided alternative hypothesis at a significance level of 0.05. The output restates all of the parameters entered, which you should quickly glance over for any errors. And at the very top, we see that the sample size required is approximately 44 subjects. The note at the bottom does state that the sample size is the required count for each group, not in total. In the third lecture, when you got a first look at the data collected, you noticed a few problems that needed to be fixed before the data can be analyzed. Let's first read in the data and attach the variable names. The first problem encountered was that some of the males were coded with a capital M and some with a small m. If we just type in the variable sex, we see all of the observations and at the very end, the levels. Here we notice the problem. To fix this, we can say that for any of the observations in sex, if sex equals to little m, in quotes because it is a name, we will set it to capital M. With the command table, we can make sure that the right change was made. Now there are no subjects for which sex equals to little m, so we can drop that level with the drop levels command. The second problem you came across was that there were quite a few missing observations, but they were all coded with 999 instead of NA, which is the default coding in R. To fix this problem, we will go through each of the variables: age, BMI, HbA1c and HbA1c baseline, CRP and CRP baseline, and for any observation that is coded with 999, we will set it equal to NA. Since our focus is on how the subjects changed over the year with respect to the outcome variables, we will create two new variables, HbA1c diff and CRP diff, and we will set them equal to the difference between the baseline measurement and the end of the study measurement. And our final step will be to do a log transformation on the CRP measurements, due to the fact that they have a very right-skewed distribution. We can define log CRP and log CRP baseline, and then take their difference to obtain log CRP diff. We have examined the data for problems, and we have fixed those problems easily using R. And with the new variables we have calculated, we are ready to carry out the formal analysis required to answer the research questions posed. We have covered all of the commands needed to analyze this data in previous R tutorials. So flip through your notes or review a previous tutorial. All of the tools you need are right at your fingertips. Good luck!